Hello, and welcome to today's deep dive. We have a truly incredible mission ahead of us today.
We really do.
Yeah, we're taking a journey straight into the realm of the unseen. We're going to be exploring some concepts laid out in a really fascinating stack of source material.
Hmm.
Specifically, we're looking at chapters 10 and 11 from a comprehensive physical sciences guide called Into the Unseen.
Right. And the goal today is to look completely past the visible macroscopic world.
Exactly. I mean, if you've spent any time at all studying classical mechanics, you've grown pretty accustomed to dealing with objects you can see, right?
Objects you can see, touch, track.
Yeah. Blocks sliding down inclined planes, planets tracing those elegant elliptical orbits around stars, pendulums swinging.
Predictable stuff.
The predictable stuff. But today we are leaving all of that visible mechanics totally behind. We are diving into the invisible, frantic, and just absolute chaos of trillions of microscopic particles.
It's a completely different paradigm for looking at reality.
It really is. We're going to examine how the universe handles heat, how it distributes energy, and maybe most profoundly, what dictates the relentless forward march of time itself.
And we're going to navigate all of this immense complexity without getting bogged down in overwhelming math.
Right. No heavy derivations today. We're focusing on the conceptual framework.
Which is crucial because when we shift our focus to the macroscopic rules that govern this microscopic chaos, we're entering the domains of thermodynamics, the kinetic theory of gases, and ultimately statistical mechanics.
Which sounds like a really daunting trio of subjects.
It does sound intimidating. But they are fundamentally connected to every single interaction in your everyday life. I mean, they dictate everything from how your car engine runs to why you age.
So to ground this, I want you, the listener, to visualize a really familiar scenario right now. Imagine you're holding a hot cup of black coffee in your hands on a crisp, cold morning.
Oh, the best feeling.
Right. You can physically feel that thermal energy migrating from the ceramic mug directly into your skin. Or, conversely, picture a perfectly square ice cube sitting on the pavement on a sweltering July afternoon.
Just slowly losing its structure.
Melting into a totally disordered puddle. Now, consider the underlying asymmetry of those events.
This is the big question.
Why does that puddle of water never, under any circumstances, spontaneously draw heat from the pavement, reverse the melting process, and reform into a perfect crystalline ice cube?
It just doesn't happen.
Right.
No.
Why does thermal energy seem to possess a strict one-way directional flow? Why does the ice melt while the puddle just absolutely refuses to unmelt?
That asymmetrical flow is arguably the ultimate question of modern physics.
Yeah.
And to set the tone for exactly how seriously the physical universe takes this question, our source text provides this absolutely brilliant quote from the British astrophysicist Sir Arthur Eddington.
I love this quote.
It's so good. He was writing about the foundational law that governs this exact unidirectional phenomenon, the second law of thermodynamics. Eddington wrote, and I'll quote it directly here, "The law that entropy always increases holds, I think, the supreme position among the laws of nature."
Supreme position.
Right, and he goes on, "If someone points out to you that your pet theory of the universe is in disagreement with Maxwell's equations, then so much the worse for Maxwell's equations. But if your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation."
Collapse in deepest humiliation.
He did not mince words.
No, he didn't. That phrasing really underscores the absolute unyielding nature of these principles. The universe has an accounting system, and it is notoriously unforgiving when it comes to the bookkeeping of heat and energy.
What's really fascinating here is how long it actually took humanity to formulate those bookkeeping rules.
Let alone understand the currency they were dealing with.
Exactly. For a huge portion of scientific history, humanity was operating under a completely different paradigm regarding what heat actually was.
Because our human perception relies so heavily on tactile and visual intuition, right?
Yeah, early natural philosophers attempted to model heat as a substantive physical entity. They basically postulated that heat was an invisible, weightless fluid that permeated all matter.
And they called this fluid caloric.
Caloric, yes.
Okay, let's unpack this caloric fluid model. Because if we strip away our modern understanding of atomic theory for a second, the caloric model is actually a remarkably elegant piece of deductive reasoning.
It really makes logical sense if you don't know about atoms.
Right. If you place a block of iron heated to 200 degrees directly next to a block of iron at room temperature, the thermal energy clearly migrates from the hotter body to the colder body until they reach thermal equilibrium.
To balance out.
They balance out. And if you conceptualize that thermal energy as a highly elastic, self-repelling fluid that naturally flows from a high-density reservoir to a low-density reservoir to equalize pressure, well, the observable phenomena track perfectly.
It did make profound logical sense. In fact, it was way more than just a philosophical placeholder. It was a highly functional scientific model.
They did real math with it.
They did. The caloric theory allowed early physicists to develop highly accurate mathematical models for heat conduction. Joseph Fourier's foundational equations regarding heat transfer, which engineers literally still use today, were originally derived under the assumption that heat was a conserved, flowing substance.
But the model was fundamentally flawed.
Completely flawed.
And the paradigm shift moving from conceptualizing heat as a conserved fluid to understanding it as a manifestation of mechanical motion wasn't catalyzed by abstract philosophy?
No, it was driven by the raw engineering requirements of the Industrial Revolution.
It really began in earnest with Benjamin Thompson, who was later known as Count Rumford, right around the late 18th century.
Rumford is such a great historical figure for this.
He was overseeing the manufacturing of artillery, specifically the boring out of solid brass cylinders to create cannon barrels.
Which is just a brutally mechanical process.
Brutal. You have massive horse-driven machinery forcing these heavy steel drill bits into solid brass to hollow out the core of a cannon.
The mechanical friction must have been immense.
Immense and totally relentless. And as Rumford observed the horses driving this boring machinery, he noted the staggering volume of heat generated by the friction of the bit against the brass.
They actually had to continuously submerge the operation in water to prevent the drill from melting.
Yeah, and the water would just boil continuously. Now, under the caloric theory, the friction of the drill was supposedly squeezing the caloric fluid out of the brass shavings.
Like wringing out a sponge.
Exactly like a sponge. But Rumford noticed a critical discrepancy. As long as the horses kept turning the drill, the brass continued to generate heat.
There was no exhaustion point.
None. If heat were a finite physical fluid stored within the crystalline structure of the brass, eventually that fluid would be entirely depleted. The brass would literally run out of caloric.
But it never did.
It never did. So Rumford proposed that because the generation of heat was theoretically inexhaustible as long as motion continued, heat could not possibly be a material substance.
It had to be intrinsically linked to the motion itself.
So the mechanical friction wasn't releasing a fluid. The mechanical motion was actively being converted into thermal motion.
And that realization begins to bridge the gap between pure mechanics and thermodynamics.
And then you look at Sadi Carnot a few decades later in 1824.
Carnot is fascinating because he was a French military engineer operating way before the scientific community had fully validated the existence of atoms.
He wasn't even trying to decode the fundamental fabric of reality.
No, he was just tasked with optimizing steam engines to give France an industrial and military advantage.
But merely by analyzing the flow of heat from a hot boiler to a cold condenser, he deduced the absolute theoretical maximum efficiency that any heat engine could ever achieve in this universe.
Carnot's work is staggering when you consider the theoretical limitations of his era. But the definitive empirical proof, the actual experiment that finally dismantled the caloric theory, came from James Prescott Joule in the 1840s.
Joule was meticulously precise.
Incredibly precise. In his most famous experiment, he designed a sealed, insulated apparatus containing a specific volume of water with a paddle wheel submerged inside it.
Okay.
This paddle wheel was connected via a system of pulleys to heavy lead weights outside the apparatus. As the weights fell under the influence of gravity, they turned the paddle wheel, vigorously churning the water.
So he is applying pure, measurable Newtonian mechanical work to the system.
Exactly. He knows exactly how much potential energy the falling weights are losing.
Right.
And by using incredibly sensitive thermometers, Joule measured the corresponding increase in the temperature of the water caused by the fluid friction of that paddle wheel.
And what did he find?
He proved with undeniable mathematical precision that the mechanical work done by the falling weights was directly proportional to the heat gained by the water.
There is a strict, unvarying exchange rate.
A strict exchange rate. He demonstrated that mechanical work and thermal heat were not distinct phenomena. They were mutually convertible manifestations of the exact same fundamental property: energy.
The caloric fluid was a phantom. Heat was merely a mechanism of energy transfer.
Exactly.
Now that we have redefined our core subject from an invisible fluid to the transfer of energy, Our source materials emphasize that we really need to establish a rigorous framework for how we observe this energy.
Right, because if we were going to study the thermodynamics of an engine or a star, we cannot attempt to model the entirety of the universe simultaneously.
We'd go crazy. We have to establish defined boundaries.
That's a critical foundational step. To apply mathematical rigor to a thermodynamic problem, we must divide reality into two distinct, non-overlapping domains.
Okay, what's the first one?
First, we define the system. The system is the specific, localized region of space or quantity of matter that we have chosen to analyze.
So this could be the combustible air-fuel mixture inside a single cylinder of a car engine.
Yes, or the liquid nitrogen inside a cryogenic dewar, or simply a single microscopic biological cell.
Which means the second domain is literally everything else.
Everything else. The surroundings.
The surroundings. This represents the entirety of the universe external to our defined system, and the interface that separates the system from the surroundings is the boundary.
Right, and that boundary can be a physical barrier, like the thick steel wall of a pressure vessel.
Or it can be a purely mathematical conceptual surface that we just define in 3D space.
Yes, and the nature of that boundary dictates the behavior of the system. Our sources categorize these boundaries into three specific thermodynamic models.
Let's go through them.
The first is the open system. In an open model, the boundary is permeable to both mass and energy.
Give us an example.
The classic textbook example is a pot of water boiling on a stove without a lid. Thermal energy is continuously entering the system through the bottom of the pot via conduction from the burner.
And mass is continuously escaping the system across the upper boundary in the form of water vapor.
Exactly.
And to ground this in human terms, you, the listener, operate as a highly complex open system.
We all do.
You ingest physical mass in the form of food and water, you expel mass via respiration and perspiration, and you are in a constant state of thermal energy exchange with the room around you.
Absorbing ambient heat or radiating your own metabolic heat away.
Okay, so that's open. What's the second classification?
The closed system. Here, the boundary is entirely impermeable to mass, but remains permeable to energy.
Impermeable to mass, permeable to energy.
Okay, a straightforward example would be a sealed, rigid cylinder of gas being heated by a flame. The quantity of gas molecules inside the cylinder remains absolutely constant.
No mass crosses the boundary.
Right. However, thermal energy readily conducts through the metal walls, increasing the internal temperature of the gas.
Makes sense. And finally, we arrive at the isolated system.
The ultimate isolation.
This is a highly idealized construct where the boundary is perfectly impermeable to both mass and energy. Nothing enters and nothing leaves.
The closest approximation we have in the macroscopic world might be a highly engineered, vacuum-sealed cryogenic flask.
Like a really, really good thermos.
A perfect thermos. If you introduce a hot liquid into a perfectly isolated system, its thermal energy cannot conduct, convect, or radiate into the surroundings.
It would theoretically maintain that exact temperature into eternity.
Theoretically, yes. While perfect isolation is practically impossible to achieve in a laboratory setting due to inevitable microscopic energy leaks, it is mathematically crucial.
Crucial for the models.
In fact, cosmologists frequently model the entire universe as a single, isolated system, operating under the assumption that there is no outside environment for mass or energy to interact with.
Okay, so having established our boundaries, we now face a measurement problem.
A huge measurement problem.
If we define a closed system, say a sealed balloon filled with helium gas, we know that we are dealing with an astronomical number of discrete atoms.
All moving with unique, highly variable kinetic energies, constantly colliding and rebounding.
We cannot possibly define the state of the system by mapping the individual momentum vector of every single atom. We'd need a computer the size of a galaxy.
Which necessitates the use of state variables.
State variables, let's define those.
These are the macroscopic aggregate properties that describe the overall thermodynamic condition of the system at a specific moment in time. They are path-independent.
Meaning they describe the current state of the system regardless of the historical thermodynamic processes that brought it to that state.
Exactly. How it got there doesn't matter, just where it is now. The four primary variables highlighted in the text are pressure, volume, temperature, and internal energy.
Let's briefly codify those for the listener.
Okay, pressure, denoted as P, is the macroscopic manifestation of the cumulative force exerted by microscopic particle collisions against the boundary of the system per unit area.
So the bouncing against the walls.
Right. Volume V is simply the three-dimensional spatial extent of the system. Temperature, T, serves as an operational measure of the average translational kinetic energy of the constituent particles.
The average speed, essentially.
Broadly speaking, yes. And internal energy, represented by U, is the comprehensive summation of all microscopic energy modalities within the system.
So this includes the kinetic energy of the particle's motion, as well as the potential energy stored within their chemical bonds and intermolecular forces.
Everything inside the box.
Right. So armed with these state variables, we're equipped to enter what the source material playfully but quite accurately refers to as the cosmic casino.
I love that analogy.
It's so good. This is the framework of the 4 laws of thermodynamics. It is an exploration of the absolute constraints placed upon the transfer and utilization of energy.
The casino analogy is incredibly precise because it perfectly illustrates the concept of insurmountable systemic constraints.
The house always wins.
The thermodynamic house always wins. Regardless of the ingenuity of the engineer or the complexity of the machine, the house ultimately dictates the outcome of every interaction.
Let's begin with the foundational premise, famously known as the 0th law of thermodynamics.
The law establishing the criteria for thermal equilibrium.
Now, before we delve into the physics of the 0th law, I always find the nomenclature absolutely fascinating.
It's a great story.
We have a robust, globally recognized framework featuring the 1st, 2nd, and 3rd laws, and yet sitting at the very foundation is a law numbered 0. It really speaks to how science actually evolves in practice versus theory.
It is a wonderful historical quirk. The 1st and 2nd laws were formalized in the mid-19th century and rapidly became the bedrock of physical chemistry and engineering. However, by the early 20th century, physicists realized they had constructed this magnificent mathematical edifice regarding energy transfer, but had never actually formalized the foundational logical axiom that allowed them to define temperature mathematically in the first place.
They skipped step 1.
They did. They needed a law that preceded the first law.
And rather than renumbering the entire established canon of thermodynamics, which would have generated immense confusion in all the literature,
they simply inserted it at the beginning and designated it the 0th law.
So what does this foundational axiom state that was so incredibly implicit they initially just overlooked it?
The 0th law states that if thermodynamic system A is in thermal equilibrium with system B, meaning there is no net transfer heat between them, implying they are at the same temperature.
Okay, A equals B.
Right. And system B is simultaneously in thermal equilibrium with a 3rd system C.
B equals C.
Then system A is unequivocally in thermal equilibrium with system C.
A equals C. In purely mathematical terms, it's the transitive property of equality applied to thermodynamics. If A equals B and B equals C, then A must equal C.
Exactly.
It sounds almost tautological, like, obviously. Why is that worthy of a fundamental law?
Because without that explicit transitive property, the entire concept of thermometry, the ability to physically measure temperature, is empirically invalid.
Ah, explain that.
Consider a standard mercury thermometer. The thermometer is system B. You calibrate system B against a known standard, perhaps the freezing point of water, which is system C.
You establish equilibrium there.
Yes. Later, you place that thermometer into a chemical solution, system A. When the mercury stops expanding, system A and system B are in equilibrium.
Right.
The 0th law is the sole logical justification that allows you to confidently state that the chemical solution, system A, shares a specific thermal relationship with the original freezing water standard, system C. Without it, temperature is not a universally quantifiable metric. In the context of the cosmic casino, the 0th law dictates the minimum requirement for participation.
You must possess a defined, measurable temperature, and you are subject to the mechanics of equilibrium.
You have to play the game.
You have to play the game. Okay, so we are seated at the table. The game has commenced. This brings us to the 1st law of thermodynamics, which dictates the fundamental economics of the universe, the conservation of energy.
The cosmic bank account.
Right. The principle states that energy can neither be created ex nihilo nor destroyed into nothingness. It can only be transformed from one modality to another or transferred from one system to another.
And the Gambler's Guide summarizes the 1st law succinctly. You cannot win.
Let's examine the mathematical accounting of this cosmic ledger. The classical formulation is Q equals delta U plus W.
Let's break those variables down.
Yeah. Here, Q represents the net heat transferred into the system. You can conceptualize this as your energetic income. It is the thermal energy you inject into the system from the surroundings.
Like applying a heat source to a cylinder of compressed gas.
Exactly. Delta U represents the change in the system's internal energy. This is the system's internal savings account. If delta U is positive, the system is accumulating energy, typically resulting in an increase in temperature as the internal particles accelerate.
And W represents the work done by the system upon its surroundings.
These are the energetic expenditures. If the heated gas expands and physically drives a mechanical piston upward against the force of gravity, the system is performing mechanical work. That physical action requires a specific expenditure of energy.
So, to apply some basic numbers here to make it concrete, if I supply exactly 100 joules of thermal energy to my system via a heat source, my Q is 100, that energy is strictly accounted for.
Every single joule.
Every single one. The expanding gas might expend 40 joules of energy, pushing that piston upward, performing mechanical work. The remaining 60 joules do not spontaneously disappear.
They are absorbed directly into the system's internal energy, elevating the temperature of the gas. The left side of the equation must always perfectly balance the right side.
Precisely. The first law establishes an absolute unbreakable barrier against the creation of a perpetual motion machine of the first kind.
A hypothetical device that can output continuous mechanical work without an equivalent input of energy.
Right. The first law mandates that you cannot extract more energy from a system than you put into it. The cosmic ledger balances to the exact decimal. You cannot generate free energy.
You can only, at best, break even.
Break even.
Which, from a purely mathematical standpoint, seems entirely equitable, a perfectly balanced, symmetrical universe. But here is where the thermodynamic reality becomes significantly more punitive.
Very punitive.
We arrive at the second law of thermodynamics. If the first law states that you cannot win, the second law introduces a far more depressing reality.
You cannot even break even.
If we connect this to the bigger picture, the first law is solely concerned with the quantitative accounting of energy. It ensures the total amount of energy remains constant. But the second law introduces a qualitative constraint.
It dictates the directionality of energy transfer and the inevitable degradation of energy's usefulness.
The universe extracts a mandatory thermodynamic tax on every single energetic transformation that occurs.
And that tax is inevitably paid in the currency of dissipated, unusable waste heat.
Our sources highlight two historically significant formulations of the second law that illustrate this principle. The first is the Kelvin-Planck statement, which focuses on heat engines.
What does it state?
It states that it is physically impossible to construct a cyclical device that absorbs thermal energy from a single hot reservoir and converts 100% of that energy into macroscopic mechanical work.
A portion of that input energy must always be exhausted as waste heat to a colder sink.
Always. A machine operating at 100% thermal efficiency is forbidden by the universe.
And the complementary formulation is the Clausius statement, which governs refrigeration cycles. It asserts that thermal energy naturally and spontaneously flows from a region of higher temperature to a region of lower temperature. It is impossible to construct a device that operates in a cycle and produces no other effect than the transfer of heat from a colder body to a hotter body.
To force heat to move against its natural thermal gradient, you must aggressively input external mechanical or electrical work into the system.
You have to force it.
And this inherent irreversibility, this unavoidable degradation of useful energy into disorganized heat, introduces one of the most profound and far-reaching concepts in all of physics: entropy.
Represented by the state variable S.
Because every energetic transaction results in a loss of usable energy, we require a metric to quantify that degradation. At a macroscopic level, entropy is frequently described as a measure of a system's disorder, randomness, or dispersal of energy.
To elevate the conceptualization of entropy beyond simplistic analogies of disorganized physical spaces, like a messy teenager's bedroom, let's consider it through the lens of information and probability.
Okay, I like this approach.
Imagine an incredibly complex digital file. Say, a high-resolution photograph. That file represents a state of extremely low entropy. The binary data is organized into a highly specific, precisely ordered sequence to render a coherent image.
There is essentially only one sequence that produces that exact perfect image.
Right. However, if random bit flip errors are introduced into the data stream, the image degrades. It becomes noisy, pixelated, and eventually unrecognizable static.
There are nearly infinite possible arrangements of static and noise.
But only one arrangement that constitutes the pristine photograph. The universe statistically favors the static. It naturally and inexorably drives systems away from highly organized, improbable states of low entropy toward highly disorganized, highly probable states of maximum entropy.
The mathematical imperative of the second law is that the total combined entropy of an isolated system, and by extension the entire isolated universe, must continually increase over time.
Energy naturally disperses, structures decay, and thermal gradients equalize.
And this universal tendency toward disorder gives rise to something conceptually staggering: the arrow of time.
The arrow of time is a deeply philosophical consequence of thermodynamics. When we examine the fundamental equations of classical mechanics, electromagnetism, or even quantum mechanics, they are remarkably indifferent to the direction of time.
They exhibit time reversal symmetry.
Yes. If you calculate the gravitational physics of a planet orbiting a star, mathematical equations function perfectly regardless of whether time is moving forward or backward.
The mechanics are entirely reversible.
But the second law of thermodynamics explicitly breaks that symmetry. It is a fundamental physical law that possesses a strict unidirectional arrow.
That is a massive paradigm shift, though. If you observe a crystal wine glass shattering on a concrete floor, you are witnessing a drastic, rapid increase in entropy. A highly structured, low-entropy object transitions into a highly disordered, high-entropy collection of shards. If you were to watch a film of that event played in reverse, the shards spontaneously leaping off the concrete and fusing back into a pristine glass, your brain instantly rejects it as an impossibility.
It was like magic.
But fundamentally, the reversed footage doesn't violate Newton's laws of motion or the conservation of energy. It exclusively violates the second law.
The universe strictly forbids the spontaneous decrease of total entropy.
This irreversible transition from order to disorder is the physical mechanism that distinguishes the past from the future.
It is the reason we experience time as a unidirectional flow. In fact, the very act of cognition, the biological process of forming a memory within your brain, requires a thermodynamic, irreversible process.
Wow.
Storing information requires the dissipation of metabolic heat, thereby increasing the entropy of your surroundings. We can only remember the past and not the future, because the recording of the memory itself is an entropy-generating event aligned with the arrow of time.
The cosmic implication, of course, is that the universe is continuously winding down, relentlessly dispersing its energy until it eventually reaches a state of thermodynamic equilibrium.
A uniform, featureless void of maximum entropy where no further energy transfers can occur.
This theoretical end state is known as the heat death of the universe.
A bit grim, but physically sound.
Very grim. So let's pull back from the existential dread of universal heat death and apply these principles to a very grounded, everyday scenario presented in the text, the open fridge paradox.
Oh, this is a fun one.
I want to pose this to you, the listener. Imagine it is the middle of a brutal summer heat wave. Your air conditioning has failed, and the ambient temperature in your kitchen is stifling.
Sounds awful.
In an act of desperation, you open the door of your refrigerator and leave it wide open, intending to use the reservoir of chilled air inside to cool down the kitchen. Thermodynamically speaking, what is the net result of this action?
The net result is that you will actively accelerate the heating of your kitchen.
The refrigerator paradox perfectly demonstrates the inescapable constraints of the first and second laws. But explain the mechanics of that, because it feels entirely counterintuitive. You are exposing the hot room to a source of cold air.
To understand why it fails, you must view the refrigerator not as a box of cold air, but as an active heat pump.
Okay.
According to the clause's statement of the second law we just discussed, heat will not naturally flow from the cold interior of the fridge to the hot exterior of the kitchen.
Right.
To forcefully extract thermal energy from the cold interior and expel it into the warmer room, the refrigerator's compressor must perform significant mechanical work, which requires a continuous input of electrical energy from the wall outlet.
Right. The first law demands that the electrical energy doesn't just disappear. It must be accounted for.
Exactly. When the door is closed, the fridge extracts heat from its interior compartment and exhausts that heat, plus the heat generated by the electrical work of the compressor, out through the condenser coils on the back of the unit into the kitchen.
So it's already heating the kitchen slightly.
Yes. But when you open the door, you have effectively placed both the cold heat sink and the hot exhaust into the exact same thermodynamic environment.
Ah.
The fridge pulls heat out of the kitchen air, runs it through the compressor, and immediately exhausts it back into the identical air mass.
It's just fighting itself.
Exactly. However, because the compressor motor is operating continuously to try and cool an impossible volume of air, it is constantly consuming electrical energy.
that electrical energy is converted into mechanical work, and due to inherent inefficiencies, a significant portion is dissipated as waste heat.
Therefore, you are continuously adding the waste heat of the compressor motor to the thermal load of the kitchen. The total entropy of the room increases, and the temperature unequivocally rises.
So returning to our gambler's guide analogy, the Zeroth law mandates that you must play the game. The first law ensures you can never win free energy. The second law guarantees that, due to the entropy tax, you will always operate at a loss.
A house always wins.
Faced with those dismal odds, what if a thermodynamic system simply attempts to opt out? What if the goal is to extract all the thermal energy, halt all microscopic motion, and reach a state of absolute frozen stasis?
That ambition brings us to the final principle, the third law of thermodynamics.
The rule of the impossible freeze.
Exactly. As you systematically extract thermal energy from a system, the kinetic energy of its constituent particles decreases. The erratic high-speed collisions slow to a sluggish crawl.
And the theoretical absolute limit of this cooling process is absolute zero, defined as 0 on the Kelvin scale.
Or roughly negative 273.15 degrees Celsius. The third law, formalized largely by Walther Nernst, states that as the temperature of a system approaches absolute zero, the entropy of the system approaches a constant, absolute minimum value.
If a substance is a perfect, flawless crystalline structure, that minimum entropy is theoretically zero.
Theoretically. If a system could achieve absolute zero, macroscopic thermodynamics suggests that all thermal agitation would cease. The system would exist in a state of perfect, singular order.
But, true to the punitive nature of the cosmic casino, there is a fundamental caveat. The third law inherently implies that it is physically impossible to reduce the temperature of any system to exactly absolute zero in a finite number of thermodynamic operations.
You can never truly reach the finish line.
The impossibility of reaching absolute zero is intrinsically linked to the mechanics of refrigeration we just discussed, isn't it?
It is. To extract heat from a system, you must couple it with a heat sink that is at a lower temperature, allowing the thermal energy to flow down the gradient.
But to extract the final fraction of thermal energy and bring an object to exactly absolute zero,
you would require a heat sink that is hypothetically colder than absolute zero, which is a physical impossibility.
because you can't go below zero.
Right. Furthermore, as a system approaches 0 Kelvin, the specific heat capacity, the amount of energy required to change its temperature, plummets asymptotically towards zero.
This means that extracting even an infinitesimally small amount of heat requires an exponentially increasing and ultimately infinite amount of work.
Modern cryogenic laboratories utilizing laser cooling and magnetic evaporation can chill atomic gases to within a few billionths of a degree above absolute zero.
Which is mind-blowing in itself.
Truly. But crossing that final mathematical threshold is forbidden by the architecture of reality. The microscopic quantum zero-point energy ensures the jiggling never, ever truly stops.
Thus completing the gambler's guide. Because you can never reach absolute zero and entirely cease the energetic fluctuations, you cannot even quit the game. You are permanently bound by the thermodynamic constraints.
It's an incredibly robust macroscopic framework. However, classical thermodynamics, the interplay of pressure, volume, temperature, and entropy, is fundamentally a descriptive science.
It accurately predicts what will occur during an energy transfer, but it remains entirely agnostic regarding why it occurs at the fundamental particulate level.
Right, because the classical laws were derived through empirical observation of bulk matter, long before the scientific consensus accepted the existence of atoms.
To truly comprehend the underlying mechanics of heat and entropy, we must transition our perspective from the macroscopic illusion to the microscopic reality.
Here's where it gets really interesting.
We are shifting gears and moving into the realm of the kinetic theory of gases. For decades, the laws we just reviewed were treated as absolute, yet entirely empirical rules.
Physicists understood that compressing a gas increased its temperature, but the fundamental mechanism was a black box.
The kinetic theory of gases was the revolutionary paradigm shift that finally illuminated that black box. It demonstrated mathematically that our macroscopic state variables, like pressure and temperature, are not fundamental properties of reality.
They are the statistical illusion generated by the chaotic interactions of billions of submicroscopic projectiles.
To bridge the massive conceptual gap between macroscopic observation and microscopic chaos without creating intractable mathematical complexity, physicists developed a highly idealized conceptual framework known as the ideal gas model.
This model relies on a specific set of simplifying assumptions about the nature of the particles.
Let's list those out. First, we assume the gas is composed of discrete, identical point masses.
We postulate that the physical volume occupied by the molecules themselves is so infinitesimally small compared to the vast, empty volumetric space between them that the volume of the particles can be treated mathematically as zero.
Second, we assume these point masses are in a state of constant, chaotic, and completely random rectilinear motion.
They travel at immense velocities in perfectly straight lines until they inevitably collide with the boundary walls or with each other.
Third, we assume the particles are completely devoid of any intermolecular forces. They are completely antisocial.
Antisocial is a good way to put it. They exert zero gravitational attraction and zero electromagnetic repulsion upon one another. They are effectively oblivious to each other's existence, interacting exclusively during the exact moment of physical impact.
And fourth, we stipulate that all collisions, whether particle to particle or particle to boundary, are perfectly elastic.
This means that the total kinetic energy and momentum of the system are perfectly conserved during a collision. There is absolutely no kinetic energy dissipated into internal vibrational states or lost to microscopic friction.
If you accept these idealized boundary conditions, you can utilize pure Newtonian mechanics to derive the entire macroscopic behavior of a gas. Let's examine how this model redefines the concept of pressure.
Think about a balloon.
Yeah, if you inflate a heavy-duty rubber balloon, the rubber is stretched taut, pushing outward against your hands. Our macroscopic intuition registers this as a continuous static outward force.
But the kinetic theory reveals that this static force is a complete illusion.
An illusion. Inside the volumetric space of that balloon, trillions upon trillions of independent gas molecules are careening around at hundreds of meters per second.
When a single molecule impacts the inner boundary of the balloon and rebounds, it transfers a minuscule, discrete pulse of momentum to the rubber.
Mathematically, force is defined as the rate of change of momentum over time. A single molecular impact imparts an incredibly tiny force.
However, because there is an astronomically high density of particles, there are sextillions of these microscopic impacts occurring against every square centimeter of the balloon's interior every single second.
And the human sensory apparatus and even our macroscopic measurement instruments are far too slow to resolve these individual discrete impacts.
Instead, we register the aggregate time-average sum of this relentless submicroscopic bombardment as a smooth, continuous force spread over an area.
That aggregate bombardment is what we define as pressure.
And then, the theory provides an even more profound redefinition of temperature. In the caloric model, temperature was an indicator of fluid density.
In classical thermodynamics, it was merely an operational metric for equilibrium.
But the kinetic theory of gases strips away the abstraction. It reveals that temperature is not a substantive entity. It is nothing more than a direct proportional measurement of the average translational kinetic energy of the constituent particles within a system.
That is a crucial distinction. When you heat a volume of gas, you are not injecting a thermal substance into it.
You are physically transferring kinetic energy to the molecules, causing them to accelerate and translate through space at higher average velocities.
The macroscopic property we perceive as hotness is simply the localized intensity of molecular motion. Let's connect this invisible molecular kinetic energy directly to the listener's biological experience.
Okay.
Imagine you're working in a kitchen and you accidentally press your bare hand against a cast iron skillet that has been sitting over an open flame. What is actually physically occurring at the microscopic boundary between your skin and the metal?
The iron atoms comprising the skillet are bound in a solid crystalline lattice, so they cannot translate freely like gas molecules. However, because the skillet has a high temperature, those iron atoms are vibrating with extreme kinetic violence around their fixed positions.
It's vigorously jiggling.
Very vigorously. When the biological molecules of your skin, which are vibrating at a significantly lower normal body temperature, come into physical contact with the skillet, a massive transfer of kinetic energy occurs via conduction.
The violently vibrating iron atoms repeatedly slam into the slower-moving molecules of your epidermal cells, forcefully accelerating them.
This sudden, chaotic surge of kinetic energy physically disrupts molecular bonds and rapidly transfers energy to your thermoreceptor nerve endings.
Your nervous system translates this localized surge of microscopic kinetic violence into the urgent macroscopic sensation of pain and extreme heat.
When you combine the mathematical derivation of pressure as aggregate momentum transfer and temperature as average kinetic energy, you inevitably arrive at the foundational equation of state.
The ideal gas law, PV equals nRT.
Pressure multiplied by volume equals the number of moles of the gas multiplied by the universal gas constant multiplied by the absolute temperature.
It is the elegant mathematical bridge that perfectly links the measurable macroscopic world to the unseen microscopic world.
And while we are discussing the intersection of thermodynamics and biology, it's worth examining another incredibly sophisticated thermodynamic mechanism: human thermoregulation.
A sweating.
Exactly. The human body is fundamentally a highly complex chemical heat engine, operating under the exact same constraints established by Sadi-Carnot and the second law.
We established earlier that a human is an open thermodynamic system. You consume high-enthalpy fuel in the form of carbohydrates and lipids, and your metabolic pathways oxidize that fuel to generate ATP, which is ultimately utilized to perform mechanical work.
Walking, lifting, breathing.
But because the second law unequivocally forbids a 100% efficient heat engine, the metabolic conversion of chemical potential energy into mechanical work is highly inefficient.
A substantial percentage of the energy released from your food is unavoidably degraded into unusable waste heat within your core.
If your body lacked a mechanism to aggressively exhaust that accumulating waste heat into a colder thermal sink, the surrounding environment, your internal temperature would rapidly rise to lethal levels, denaturing proteins and causing catastrophic systemic failure.
Sweating is your body's brilliant evolutionary adaptation for complying with the second law. Your body actively pumps water onto the surface of the skin.
As the highest energy water molecules absorb the waste heat from your bloodstream, they gain sufficient kinetic energy to break their intermolecular hydrogen bonds and undergo a phase change from a liquid to a gas.
That phase change evaporation carries the massive payload of latent heat away from your body and disperses it into the atmosphere.
You are utilizing evaporative cooling to aggressively dump waste heat and increase the entropy of your surroundings, allowing your internal biological engine to continue operating without self-destructing.
It's a perfect application of thermodynamic principles. However, while the kinetic theory of gases provides a beautiful conceptual framework, it immediately introduces a seemingly insurmountable mathematical crisis.
The math gets too hard.
The equations work solidly for predicting the average behavior of the system, but the actual physical reality is staggeringly complex. A single standard breath of air drawn into your lungs contains approximately 10 to the 23rd individual molecules.
Yeah, it is 100,000 billion discrete particles, all moving simultaneously.
Right. And if you subscribe to a strictly deterministic Newtonian view of the universe, you should theoretically be able to calculate the exact future state of that gas by mapping the position and velocity vectors of every single molecule and calculating every single perfectly elastic collision.
But from a computational standpoint, that is a laughable impossibility. The sheer volume of interacting variables is beyond comprehension.
If you commandeered the most powerful quantum supercomputer currently in existence and tasked it with calculating the exact trajectory of every molecule in a simple cup of coffee, the computer would exhaust its lifespan before it could calculate a fraction of a millisecond of real-time particle dynamics.
The deterministic approach is hopelessly crushed by the sheer scale of the chaos. So how do physicists actually derive precise mathematical predictions from such an overwhelmingly chaotic system?
They achieve precision by abandoning determinism. They surrender to the chaos.
Surrender to it.
Instead of attempting the impossible task of tracking the precise history and future of an individual molecule, they shift their mathematical focus to predicting the aggregate behavior of the entire population. They utilize the profound power of statistics and probability.
This paradigm shift leads us to the ultimate theoretical bridge: statistical mechanics. Let's examine the logic behind statistical prediction, often referred to as the wisdom of the crowd. If you take a perfectly balanced coin and flip it a single time, the outcome is inherently unpredictable. It is a discrete binary event, 50% heads, 50% tails. The individual event yields zero predictive information.
However, if you flip that exact same coin 1 billion times, the aggregate result is incredibly predictable.
You can state with near absolute mathematical certainty that the final tally will be exceptionally close to 500 million heads and 500 million tails.
The behavior of the individual is entirely random, but the behavior of the massive aggregate crowd follows strict, unbreakable probabilistic laws.
In the latter half of the 19th century, brilliant physicists like James Clerk Maxwell and Ludwig Boltzmann realized that this exact statistical logic must apply to the chaotic swarms of atoms in a gas.
You do not need to know the specific velocity vector of molecule number 4,892,110. You only need to know the statistical probability of finding any molecule operating at a specific velocity within the massive crowd.
And this realization birthed the Maxwell-Boltzmann distribution. We established a moment ago that temperature is the average kinetic energy of the particles, but that doesn't imply a uniform distribution.
If the ambient air in a room is 20 degrees Celsius, it does not mean every single nitrogen and oxygen molecule is translating at the exact same velocity.
The collisions are constantly transferring energy, accelerating some molecules and decelerating others.
Maxwell and Boltzmann mathematically demonstrated that the velocities of the particles are distributed across a continuous spectrum, forming a highly specific statistical bell curve.
A helpful way to conceptualize this distribution without relying on simplistic analogies is to consider the distribution of price fluctuations in a highly liquid financial market.
That's a great comparison.
On any given day, the vast majority of stock prices fluctuate within a narrow, predictable average band. The central cluster represents the bulk of our gas molecules operating near the average thermal velocity.
However, the distribution has tails. At any moment, due to random compounding economic collisions, a small fraction of stocks will experience massive, volatile downward crashes, representing the molecules that have lost nearly all their kinetic energy and are moving exceptionally slowly.
Conversely, on the opposite tail of the distribution, a tiny fraction of stocks will experience explosive, high-velocity upward spikes. These represent the exceptionally fast molecules that have accumulated massive kinetic energy through a series of statistically fortunate collisions.
The overall temperature of the market is defined by the average bulk movement, but the extreme outliers always exist probabilistically.
And as you inject heat into the gas, you are shifting the parameters of that bell curve. The peak of the curve shifts toward higher velocities, and the curve itself broadens, flattening out.
The average speed increases, but crucially, the high-velocity tail of the distribution grows significantly larger. You generate a much higher population of those extreme high-energy outlier molecules.
This statistical distribution perfectly elucidates a very common phenomenon: the physics of evaporative cooling when you blow on a hot beverage.
Yes.
Why does blowing across the surface of a hot cup of coffee cause its temperature to drop so rapidly? You are actively exploiting the Maxwell-Boltzmann distribution.
The liquid coffee possesses a specific average kinetic energy, its temperature. However, the molecules occupying the extreme high-velocity tail of the statistical distribution possess enough kinetic energy to overcome the intermolecular forces holding the liquid together.
They break the surface tension and escape into the air above the cup as vapor. This is the mechanism of evaporation.
And when you blow across the surface, you are physically sweeping away that localized cloud of high-energy escaped vapor.
By removing those energetic molecules from the immediate boundary layer, you prevent them from colliding with the surface and re-entering the liquid.
Because the highest energy molecules are continually escaping, the average kinetic energy of the remaining liquid must decrease. To maintain its thermodynamic equilibrium and repopulate the high-velocity tail of its statistical distribution, the liquid is forced to promote a new batch of molecules to evaporate.
You are systematically and continuously draining the highest energy statistics from the population, forcing the overall temperature to plummet.
It is a phenomenal demonstration of statistics dictating macroscopic reality. But Ludwig Boltzmann did not stop at mapping velocities.
He pushed the statistical framework to its absolute philosophical limit, culminating in what is widely considered one of the most elegant and profound equations in all of physics: S equals K log W.
Boltzmann achieved a monumental conceptual leap. He took the macroscopic, somewhat nebulous concept of entropy, which classical thermodynamics defined merely as the ratio of heat transfer to temperature, and rigorously redefined it as a pure function of statistical probability.
This equation is so incredibly foundational to our understanding of the universe that it is literally carved into Boltzmann's tombstone in Vienna.
Let's unpack the variables in S equals K log WAS represents the total macroscopic entropy of the system.
K is the Boltzmann constant, which is a fundamentally tiny value that serves as the crucial mathematical scaling factor, translating the energetic behavior of single microscopic atoms into the macroscopic units we observe.
Log represents the natural logarithm, scaling massive numbers into manageable proportions. And finally, W represents the number of microstates.
The distinction between macrostates and microstates is the absolute core of statistical mechanics.
The macrostate is the aggregate, observable condition of the system, defined by our state variables, a specific pressure, volume, and temperature.
The microstates, denoted by W, are the specific, detailed microscopic arrangements of the individual particles. They're precise positions and momenta that can combine to produce that exact identical macrostate.
To make this abstract concept concrete for the listener, let's use an analogy involving combinatorial probability. Imagine you have a highly ordered, sequential deck of playing cards, freshly opened from the manufacturer.
Spades, hearts, clubs, diamonds, all arranged from ace to king.
This specific sequential arrangement is the macrostate. How many possible microstate-specific arrangements of the 52 individual cards result in this exact sequential order? Exactly 1. W equals 1.
The probability of this state occurring randomly is astronomically low. It is a state of minimum entropy.
Now imagine you thoroughly shuffle the deck several times. You examine the deck, and it's a randomized, unstructured sequence of mixed suits and numbers. The macrostate is now randomly shuffled.
How many possible microstates' unique, distinct orderings of the 52 cards result in a deck that appears randomly shuffled to the observer?
The answer is practically infinite. There are 52 factorial possible arrangements, which is a number so large it exceeds the number of atoms in the Earth. The vast, overwhelming majority of those combinations look like a random, disordered mess.
And this leads directly to Boltzmann's ultimate revelation regarding the second law of thermodynamics. Why does a concentrated drop of blue dye slowly disperse and diffuse uniformly throughout a beaker of clear water instead of spontaneously aggregating back into a single dense drop?
It is not driven by some invisible, repulsive physical force. It is driven purely by combinatorial probability.
There is only a minutely small number of microstates where all the dye molecules happen to be localized in one specific corner of the beaker. But there are trillions upon trillions of microstates where the dye molecules are distributed evenly among the water molecules.
As the molecules randomly collide and shift positions, the system is overwhelmingly more likely to wander into a macrostate that is supported by the highest number of microstates. The system inevitably evolves toward maximum W.
Boltzmann proved that the inexorable increase of entropy dictated by the second law is not an unbreakable, fundamental mechanical barrier. It is simply a statistical certainty.
A shattered glass resting on a concrete floor could theoretically reassemble itself. If every single atom in the shards in the surrounding environment happened to undergo a simultaneous, perfectly coordinated sequence of collisions that exactly reverse the trajectory of the shattering event, the glass would reform.
It does not violate the conservation of energy or Newtonian mechanics.
However, the probability of that specific highly ordered microstate occurring purely by random chance is so infinitesimally close to zero that you could observe the universe for 1 trillion times its current age and never witness it occur.
Entropy increases because disorder is statistically overwhelmingly more probable than order.
But the historical narrative surrounding Ludwig Boltzmann and his monumental discovery is profoundly tragic. You would assume that a physicist who successfully decoded the mathematical mechanism behind the arrow of time would be universally celebrated by his peers.
However, the scientific landscape of the late 19th century was fiercely ideologically divided. Boltzmann was a staunch atomist. His entire statistical framework relied absolutely on the premise that matter was composed of discrete, physical, submicroscopic particles.
And that premise was highly controversial. The dominant faction in European physics at the time was the energeticists, championed by incredibly influential figures like Wilhelm Oswald and the philosopher-physicist Ernst Mach.
It is crucial to understand that Mach and Oswald were not simply being obstinate or malicious. They were operating under a strict philosophical framework of logical positivism and extreme empiricism.
They argued that science should solely concern itself with macroscopic, measurable phenomena like energy, work, and observable thermodynamics.
Right.
Because no one had ever seen an atom and there was no definitive empirical proof of their physical reality, Mach argued that atoms were merely a convenient, unproven mathematical fiction.
To base the fundamental laws of thermodynamics on the hypothetical behavior of invisible entities was, to the energeticists, a violation of rigorous scientific methodology.
They fundamentally rejected the idea that the absolute unyielding laws of physics were based on nothing more than probability. They viewed statistical mechanics as an unstable foundation.
Boltzmann faced relentless intellectual opposition. His statistical theories were frequently rejected, heavily criticized at major scientific conferences, and marginalized by the academic establishment.
Boltzmann, who suffered from severe cyclical bouts of depression and anxiety, internalized this intense academic friction.
The persistent rejection by his esteemed peers, combined perhaps with the immense philosophical weight of his own deterministic conclusions, that the universe was a mechanized system inevitably decaying toward a cold, lifeless, thermodynamic equilibrium, took a devastating toll on his mental health.
Tragically, in 1906, while vacationing with his family in Italy, Boltzmann took his own life.
It is one of the most heartbreaking chronologies in the history of science, particularly because of what happened immediately afterward. Boltzmann died believing his life's work had been largely rejected by the consensus.
Yet just 1 year prior to his death, in 1905, a young patent clerk named Albert Einstein published a paper on Brownian motion, the erratic, jittery movement of microscopic pollen grains suspended in water.
Einstein utilized Boltzmann's exact statistical methods to definitively prove that the pollen grains were being physically bombarded by discrete, invisible water molecules.
Shortly following Boltzmann's death, experimentalist Jean Perrin conducted the precise measurements Einstein suggested, proving unequivocally that atoms were real, physical entities.
The energeticist opposition collapsed. Boltzmann's statistical framework was entirely vindicated and became the cornerstone of modern physics, but he did not live to witness his own triumph.
It is a sobering reminder that the progression of science is a deeply human endeavor, fraught with intellectual bias, philosophical friction, and immense personal cost.
But despite the tragedy, Boltzmann's statistical lock on the behavior of the universe proved to be mathematically absolute, which naturally meant that the next generation of theoretical physicists immediately dedicated themselves to figuring out how to pick that exact lock.
Physicists love a challenge.
They really do. This brings us to Section 5, and what is arguably one of the most famous and frustrating thought experiments in the history of thermodynamics, Maxwell's demon.
The demon is a brilliant conceptual challenge. In 1867, James Clerk Maxwell, the physicist who co-developed the statistical distribution we discussed earlier, posed a profound question to his colleagues. What if intelligence, rather than brute mechanical force, could be utilized to subvert the second law of thermodynamics?
He designed a thought experiment to test the absolute limits of entropy. Let's construct the demon's apparatus for the listener. Imagine a perfectly insulated, isolated container. We divide this container directly down the center with a solid, impermeable partition, creating two equal chambers, room A on the left and room B on the right.
Both chambers are initially filled with the exact same elemental gas, and both are in perfect thermal equilibrium at the exact same temperature.
Therefore, according to the Maxwell-Boltzmann distribution, both room A and room B contain a vast, chaotic mixture of high-velocity hot molecules and low-velocity cold molecules evenly dispersed.
Now, Maxwell introduces a modification. He cuts a tiny microscopic aperture into the central partition, creating a door just large enough for a single gas molecule to pass through. And guarding this aperture is a hypothetical, microscopic entity endowed with immense cognitive processing power and incredibly fast reflexes. The demon.
The demon operates a perfectly frictionless shutter over the aperture.
The demon's operational protocol is simple but highly specific. It monitors the trajectories of the molecules approaching the partition. If the demon observes a high-velocity, energetic molecule approaching from room A, it swiftly opens the frictionless door, allows the hot molecule to transit into room B, and instantly closes it.
Conversely, if it observes a low-velocity, sluggish molecule approaching from room B, it opens the door to let it transit into room A.
It is crucial to remember the parameters. The door is completely frictionless, and the molecules are not being mechanically forced. They are moving under their own kinetic power. Therefore, the demon is performing practically zero macroscopic physical work upon the system.
But observe the macroscopic result of the demon's continuous sorting algorithm. Over time, room B accumulates an overwhelming concentration of high-velocity molecules, while room A is left with the low-velocity molecules.
Without the input of mechanical work, the demon has caused room B to become boiling hot, while room A becomes freezing cold,
which completely shatters the fundamental tenets of thermodynamics. The Cauchy statement of the second law explicitly states that thermal energy cannot spontaneously flow from a colder region to a hotter region without the input of external work.
The demon has taken a high-entropy, uniformly mixed gas in thermal equilibrium and spontaneously segregated it into a highly ordered, low-entropy thermal gradient.
It has generated a massive temperature differential out of thin air, which could theoretically be used to drive a turbine and generate infinite free energy. The demon has broken the universe.
This thought experiment presented a terrifying paradox. This raises an important question. Where is the fundamental flaw in Maxwell's logic? If the demon doesn't exert physical force, why does the second law remain intact?
For nearly a century, brilliant physicists scrutinized the mechanics of the door, the quantum uncertainty of the molecules, and the thermal radiation of the demon itself, searching for the hidden energy cost.
The ultimate resolution, conceptualized by Leo Szilard in the 1920s and rigorously formalized by IBM researcher Rolf Landauer in 1961, required a revolutionary convergence of thermodynamics and the nascent field of computer science. The demon's fatal flaw resides entirely within its cognitive processes.
The demon is not a purely mechanical construct. It is an information processing system. To execute its sorting algorithm, the demon must first measure the velocity of an incoming molecule. It must acquire data.
It then has to store that specific velocity data in its internal memory to calculate whether to open or close the door. And most critically, because the demon's memory capacity must necessarily be finite, it has to actively erase that stored data to clear the memory register for the next approaching molecule.
And this sequence leads to the formulation of Landauer's principle, a monumental discovery that permanently fused information theory with physical thermodynamics.
Landauer demonstrated that information is not a purely abstract mathematical concept. Information is fundamentally physical. Any logically irreversible manipulation of information, specifically the erasure of a bit of data or the resetting of a memory register, must necessarily be accompanied by a physical increase in the thermodynamic entropy of the processing system and its surroundings.
Erasing information is an irreversible physical process that requires the dissipation of energy in the form of heat.
And Landauer provided a precise mathematical equation for the absolute minimum thermodynamic cost of data erasure, E equals K T ln 2.
Let's break that down because it is the cost of computation itself. E is the minimum energy dissipated as heat. K is our familiar Boltzmann constant linking the micro to the macro. T is the absolute temperature of the computing system.
And A is the natural logarithm. And 2 represents the two possible binary states of the data, bit a 0 or a 1, that is being irreversibly compressed or erased.
Every single time the demon erases the velocity data of a molecule from its memory to process the next event, it pays an unavoidable thermodynamic tax mandated by Landauer's principle. It generates a discrete microscopic pulse of waste heat.
Because the demon is processing billions of molecular trajectories per second, its brain is continuously dissipating massive quantities of thermal energy into the gas.
By the time the demon has successfully sorted the hot and cold molecules, decreasing the entropy of the gas chambers, the cumulative waste heat generated purely by its cognitive data erasure has increased the total entropy of the system by an amount that is equal to or strictly greater than the order it created.
The demon ultimately defeats itself through the physical cost of computation. The second law remains mathematically supreme.
I want to ground this incredible theoretical concept in the physical reality of the listener. This is not just an abstract paradox regarding microscopic demons. Landauer's principle dictates the thermal limits of modern computing architecture.
It absolutely does.
When you are holding your smartphone and you select an old high-resolution photograph and permanently delete it from the solid-state memory drive, you are executing an irreversible erasure of physical information.
According to the strict laws of thermodynamics, the physical act of deleting that specific arrangement of digital bits fundamentally requires the dissipation of energy. Deleting that photo literally, measurably, ever so slightly, warms up the silicon processor in your device.
Information processing is intrinsically linked to physical entropy.
It is a profound realization that the abstract manipulation of data has an inescapable thermal footprint. However, the resolution of Maxwell's demon also reinforced a practical reality. It is computationally unfeasible to track individual particles.
If a theoretical superintelligence overheats and fails simply trying to sort a few molecules, how can human physicists possibly calculate the thermodynamic properties of billions of interacting particles without their own mathematical models collapsing into intractable complexity?
The solution was to stop analyzing the system as a collection of individual particles moving through physical space, and instead invent an entirely new, hyperdimensional mathematical architecture.
Which brings us to the mathematical multiverse, pioneered by Josiah Willard Gibbs. Gibbs was an incredibly brilliant yet remarkably unassuming American mathematical physicist operating in the late 19th and early 20th centuries.
He realized that the sheer computational friction of tracking molecular collisions over time was insurmountable. If you want to calculate the average pressure of a gas inside a container over a 1-minute interval, The standard deterministic approach requires you to take a time average.
You measure the state at millisecond 1, calculate the billions of collisions to find the state at millisecond 2, and so on, integrating over time.
Gibbs recognized that time was the primary obstacle. So, in an act of mathematical audacity, he simply removed time from the equation altogether.
To accomplish this, Gibbs developed the conceptual framework of phase space. To understand phase space, we must first look at a single particle. To completely define the physical state of one individual atom moving freely in three-dimensional space at a frozen moment in time, you require exactly 6 numerical coordinates.
You need 3 coordinates to define its precise spatial position, the x, y, and z axis. And you need 3 additional coordinates to define its momentum, its velocity, and mass moving along those exact same x, y, and z axes.
Therefore, the complete state of a single atom can be represented as a single point within a mathematical space that possesses exactly 6 dimensions.
Now, scale that up. If you have a macroscopic thermodynamic system, like a sealed liter of oxygen gas, you have roughly 10 to the 23rd particles.
To define the exact precise state of that entire macroscopic system at one single frozen instant in time, you must specify the 6 coordinates for every single molecule simultaneously.
This means the overall state of the entire system is represented by a single, solitary point moving through an abstract, hyperdimensional mathematical space that possesses 6 n dimensions, where n is the number of particles.
That equates to a continuous mathematical manifold containing roughly 600 billion trillion independent dimensions. It is an architecture that completely defies human visual intuition, but mathematically it is perfectly rigorous.
As the gas molecules continuously collide and exchange momentum, the macroscopic system constantly changes its internal configuration. In Gibbs' framework, this evolving system is represented by that single point, tracing an unimaginably complex, chaotic trajectory through the 6n-dimensional phase space as time progresses.
But Gibbs still faces the time problem. Tracking that single point as it wanders through 600 billion trillion dimensions over time is mathematically just as impossible as tracking the physical atoms. This is where Gibbs introduces his genius workaround, the statistical ensemble.
Instead of attempting to watch one single thermodynamic system evolve over a period of time, Gibbs hypothesized an infinite theoretical collection of parallel universes.
Imagine infinite mental clones of your macroscopic system. Each clone is subjected to the exact same macroscopic boundary conditions, the same total volume, the same total energy.
However, within each parallel clone, the microscopic particles are arranged in a completely different, unique configuration. Every single possible microstate, every conceivable permutation of atomic positions and momenta that could possibly exist within those constraints, is realized simultaneously across this infinite collection of parallel systems.
This vast conceptual collection of simultaneous states is what Gibbs defined as an ensemble, all frozen in one single instant.
And the brilliance of the ensemble relies on a principle called the ergodic hypothesis. Gibbs posited that instead of calculating the time average of a single system as it slowly wanders through all its possible configurations over an eternity, you can simply calculate the ensemble average.
You mathematically average the properties of all the infinite parallel universes existing simultaneously at one frozen moment. Because the ensemble contains every state the single system would eventually visit over infinite time, the ensemble average yields the exact same mathematical result as the time average.
He completely bypassed the necessity of tracking collisions through time.
It is a triumph of statistical abstraction. Gibbs formalized 3 primary categorizations of these ensembles to model different boundary conditions.
The first is the microcanonical ensemble, which represents our isolated systems. In this ensemble, every single parallel universe possesses the exact same, strictly conserved total energy, volume, and number of particles.
The second is the canonical ensemble, representing closed systems. Here, the parallel universes are allowed to exchange energy with a massive theoretical thermal bath, meaning their individual energies can wildly fluctuate, but they all share the exact same average temperature.
And finally, the grand canonical ensemble, which models open systems where both energy and particles are continuously fluctuating in and out of parallel universes, sharing a common temperature and chemical potential.
So what does this highly abstract, multidimensional mathematics actually achieve? It provides the computational foundation for modern engineering.
The statistical ensembles that Gibbs formulated allow engineers and physicists to calculate with extreme precision the thermodynamic properties of highly complex systems without ever tracking a single atom.
It is the math used to optimize the superheated steam turbines in nuclear power plants and to model the quantum behavior of billions of electrons migrating through the semiconductor lattice of a silicon microchip.
Classical thermodynamics, bolstered by the statistical rigor of Boltzmann and Gibbs, forms an incredibly reliable and robust framework for understanding the mechanics of our immediate reality. The equations work flawlessly from the scale of a combustion engine down to the interactions of a biological cell.
However, physics is fundamentally driven by exploring boundaries. We must inevitably ask, what happens when we push these seemingly absolute thermodynamic laws away from the comfort of our macroscopic environment and into the absolute universe-breaking extremes of reality?
Which transitions us to the final frontier of our deep dive, the extreme edges. When we push physical systems to the absolute limits of temperature and gravity, classical Newtonian mechanics and classical thermodynamics begin to warp.
They interface with our two most complex and notoriously incompatible frameworks of reality: quantum mechanics, which governs the incredibly small, and general relativity, which governs the immensity of gravity. Let's examine the edge of cold first.
We established under the third law that it is impossible to reach absolute zero. However, we also established that experimentalists can utilize advanced techniques to cool dilute clouds of atomic gas to temperatures that are fractions of a billionth of a degree above 0 Kelvin.
In the 1920s, utilizing the statistical mechanics frameworks we just discussed, Satyendranath Bose and Albert Einstein predicted that at these ultra-cold extremes, the classical kinetic theory of gases, the idealized model of independent bouncing billiard ball particles, would experience a catastrophic breakdown.
As the thermal energy of the atoms is aggressively stripped away, their velocity approaches 0. And according to the principles of quantum mechanics, specifically the de Broglie wavelength, as a particle's momentum decreases, its quantum mechanical wave function, the probability wave that dictates its physical location, begins to physically spread out and expand.
In a classical gas, the atoms are distinct, separate entities because their wave functions are small and highly localized. But as the temperature plunges toward absolute 0, these individual atomic wave functions expand significantly.
Eventually, the wave functions become so large that they begin to physically overlap with the wave functions of adjacent atoms. At a specific critical temperature, a profound phase transition occurs.
The individual wave functions of millions or even billions of atoms merge entirely. They snap into a single, unified quantum state occupying the lowest possible energy level. They lose all individual identity and behave as a single macroscopic superatom.
This phenomenon is known as a Bose-Einstein condensate, or a BEC. It is widely considered a distinct fifth state of matter, fundamentally different from a solid, liquid, gas, or plasma.
And because this macroscopic clump of matter is operating under a single quantum wave function, it exhibits deeply bizarre, non-classical behaviors. Certain Bose-Einstein condensates become superfluids.
A superfluid possesses exactly 0 internal viscosity. It experiences 0 kinetic friction. If you place a superfluid inside a beaker and set it spinning, it will theoretically spin forever without losing any kinetic energy to heat.
Furthermore, due to quantum mechanical boundary conditions, a superfluid will spontaneously creep up and over the vertical walls of the beaker, effectively defying classical gravity to find a lower energy state.
The strict, chaotic thermodynamic rules of the macroscopic world are entirely overwritten by coherent quantum weirdness.
It represents the triumph of quantum mechanics at the low energy extreme. Now, let us pivot sharply to the exact opposite extreme, the edge of hot, heavy, and dense. We must examine the intersection of thermodynamics and the ultimate gravitational anomalies, black holes.
Regions of spacetime where the concentration of mass is so extreme that the gravitational acceleration exceeds the speed of light, rendering the event horizon a boundary of absolute no return.
In the early 1970s, the theoretical physicist Jacob Bekenstein realized that the classical conceptualization of a black hole presented a massive, potentially fatal paradox for the second law of thermodynamics.
Bekenstein posed a theoretical scenario that was elegant in its simplicity, but devastating in its implications. Suppose you are in orbit around a black hole, and you hold in your hand an object possessing a high degree of thermodynamic entropy. Let's return to our hot, chaotic, structurally disordered cup of coffee.
You throw the cup of coffee directly into the black hole. It crosses the event horizon. According to the tenets of general relativity, nothing can escape the event horizon. The mass and the information contained within the coffee cup are permanently removed from the observable universe.
Bekenstein asked, did the total entropy of the observable universe just decrease?
If the black hole simply absorbs the entropy and locks it away forever without exhibiting any external thermodynamic change, it is acting as a cosmic entropy vacuum.
It would provide a reliable mechanism for systematically reducing the entropy of the universe, which is a direct catastrophic violation of the second law.
Bekenstein theorized that to save the second law, the black hole itself must possess entropy, and the entropy of the black hole must increase when it absorbs the coffee cup. He proposed that the entropy of a black hole is directly proportional not to its volume, but to the surface area of its event horizon.
Initially, this proposal was met with extreme skepticism, most notably by young Stephen Hawking. Hawking argued, utilizing classical thermodynamics, that if a black hole possesses entropy, it must inevitably possess a temperature.
And according to the established laws of thermal radiation, any object that possesses a temperature above absolute zero must continuously radiate heat into its surroundings.
But the fundamental definition of black hole is that its gravitational field prevents all radiation, including massless photons, from escaping. Therefore, Hawking reasoned, black holes cannot radiate heat, therefore they cannot have a temperature, therefore Bekenstein's theory of black hole entropy must be incorrect.
However, the scientific paradigm shifted dramatically when Hawking decided to apply the principles of quantum field theory to the curved space-time immediately surrounding the event horizon.
The quantum mechanical model of a vacuum is not an empty void. It is a bubbling, turbulent sea of quantum fluctuations. According to the Heisenberg uncertainty principle, pairs of virtual particles, specifically a particle and its corresponding antimatter antiparticle, are continuously popping into existence from the vacuum.
They borrow a minute amount of energy from the universe and then instantly collide and annihilate each other, returning the borrowed energy in a timescale so incredibly short that it violates no conservation laws.
This pair production is occurring constantly everywhere in the universe. But Hawking realized that a unique boundary condition occurs directly on the razor-thin mathematical edge of a black hole's event horizon.
If a pair of virtual particles spontaneously materializes exactly on the horizon, the immense gravitational tidal forces can violently separate them before they have the opportunity to mutually annihilate.
One particle is dragged across the event horizon and falls into the singularity. The other particle, positioned just outside the horizon, is violently accelerated outward and escapes into the surrounding cosmos as a real, observable particle.
And this mechanism resolves the paradox. The escaping particle requires real, positive energy to become a permanent fixture of reality. Because energy must be strictly conserved according to the first law, the escaped particle must steal that requisite energy directly from the gravitational mass of the black hole itself.
This continuous stream of escaping quantum particles constitutes what is now known as Hawking radiation.
It was one of the most astonishing theoretical discoveries in modern astrophysics. It proved that Bekenstein was absolutely correct. Black holes are not completely black. They emit a faint, incredibly low-temperature thermal glow.
And because they are actively radiating thermal energy into space, they are very, very slowly losing mass. Over unimaginable trillions of years, a black hole will eventually evaporate entirely.
So returning to Bekenstein's coffee cup, when you throw the high-entropy cup into the abyss, the mass of the coffee cup slightly increases the total mass of the black hole, which slightly expands the total surface area of the event horizon.
That increase in the surface area of the event horizon perfectly encodes the added entropy, ensuring the total entropy of the universe increases. The second law of thermodynamics is saved.
Even in the presence of the ultimate, universe-crushing gravitational anomalies, the laws of thermodynamics maintain absolute, terrifying power.
It is a phenomenal synthesis of the macroscopic and the quantum realms. We have traversed an incredible breadth of physical reality today. We began by examining the macroscopic empirical laws of classical thermodynamics, the strict accounting ledger of the first law, ensuring the conservation of energy, and the unavoidable unidirectional tax levied by the second law, driving the relentless increase of entropy.
We then shifted our perspective to decode the underlying mechanics, delving into the kinetic theory of gases. We discovered that the macroscopic forces we experience daily, the steady pressure of the atmosphere, the intense temperature of a stove, are merely the statistical illusions generated by the chaotic, high-velocity collisions of trillions of microscopic particles.
We explored the immense computational problem of tracking those particles and how Boltzmann and Gibbs revolutionized physics by embracing probability in statistics, translating the thermodynamic arrow of time into a mathematical certainty.
We observed how those statistical models established the physical limits of information processing through Maxwell's demon and Landauer's principle, proving that computation is fundamentally thermodynamic.
And finally, we tested these unyielding laws at the extreme margins of reality, witnessing the quantum macroscopic phenomena of Bose-Einstein condensates near absolute zero, a mind-bending intersection of quantum mechanics and gravity at the evaporating event horizons of black holes.
It is a staggering amount of interconnected physics, but I want to bring all of this vast cosmic machinery back down to your immediate personal experience. I want you, the listener, to remember the profound implications of what we've discussed today.
It connects to everything you do.
Every single time your body sweats to maintain equilibrium during a grueling workout, every time you blow across the surface of a hot beverage, actively manipulating a statistical distribution of molecules, and incredibly, every time you tap a screen to permanently delete a photograph from a silicon memory drive, dissipating microscopic heat into the environment.
You are actively participating in the grand, chaotic, statistical machinery of the universe.
The invisible microscopic mechanics are entirely dictating the visible reality you navigate every day.
It is deeply humbling to realize our absolute integration into these processes. And as we conclude our deep dive into the unseen, I want to leave the listener with one final, deeply provocative philosophical consideration drawn directly from the analytical exercises in our source text. It concerns the tension between deterministic classical mechanics and the probabilistic nature of modern physics.
We have spent significant time discussing how we must rely on statistical probabilities to predict the behavior of complex systems because human computational power is vastly insufficient to track the specific trajectory of 10 to the 23rd independent atoms.
We surrender to the statistical chaos as a matter of practical necessity.
But consider a scenario where practical limitations do not exist. Imagine a theoretical superintelligence, a hypothetical computing entity often referred to in literature as Laplace's demon.
Suppose this infinitely powerful supercomputer is capable of simultaneously knowing the exact spatial position, the precise momentum, and the current trajectory of every single fundamental particle in the entire universe at this exact moment in time.
If Laplace's demon possessed all that data and perfectly understood the absolute deterministic laws of classical physics, could it calculate and perfectly predict the entirety of the future?
And conversely, could it run the mathematical models in reverse to perfectly reconstruct every event in the past?
Does the universe actually function like an unimaginably complex but strictly deterministic clockwork mechanism, playing out a rigid, inevitable script where our perception of chaos is merely a symptom of our own ignorance?
Or does the underlying architecture of reality reject determinism entirely? Does the universe's fundamental reliance on the statistical probabilities mapped out by Boltzmann, compounded by the inherent unresolvable quantum uncertainty that Hawking utilized to evaporate black holes, mean that the future is genuinely fundamentally unwritten?
Are we merely riding an evolving wave of probability where outcomes are never truly certain until the moment the waveform collapses and the event occurs?
That is the ultimate intersection of theoretical physics and the philosophy of free will. If macroscopic entropy is fundamentally driven by statistical probability, and the microscopic foundation of matter is governed by quantum randomness, then the rigid determinism of Laplace's demon is physically impossible.
The future remains a statistical blur, continuously being resolved into the present.
A universe that is still actively deciding what it wants to be at every moment.
That is a phenomenal concept to conclude on. Thank you so much for joining us on this massive, complex journey into the unseen mechanics of reality. We hope this deep dive ensures that you will never look at a melting ice cube, a steam engine, or even a deleted digital file in quite the same way ever again. We're going to sign off now and leave you to ponder the inevitable unidirectional arrow of time in your own life. Stay profoundly curious.